So the whole point of having pacemaker cells is that these cells will provide the electricity required to activate your other heart muscle cells, the ones which are required to squeeze the heart. Okay, so you have pacemaker cells, you have your non-pacemaker myocardial cells. These are the ones that squeeze the heart, during systole and diastole. So let's try it. So we're going to look at how this electricity spreads across the heart wall to activate the various non-pacemaker myocardial cells. So again, draw the heart. Okay. So begin here in the SA node. It's called the conduction system. How the electricity spreads across the heart. So you begin in the SA node, and it spreads across. It spreads across the atria from the SA node, through your intercalated disc, the gap junctions. So that's one SA node. Then it spreads to the AV node. Number two, the AV node. Just SA to AV node. Then the AV node will spread it into an area called your bundle of His. Bundle of His, or your atrioventricular bundle of His. Okay. Then from there, it spreads down the interventricular septum, like so. All right, so again, so spread in here, then to here. Then to your number three, so this is bundle of His. Then from there, it goes to your right and left bundle branches. We call these bundle branches. And then it goes up from the tip of the heart back up this way. What's called your Purkinje fibers. Okay, so it's SA node, AV node, bundle of His, right and left bundle branches. And then up the outside of the ventricles in what's called your Purkinje fibers. That way, the heart squeezes this way to push the blood up, not down this way. Okay, so when it squeezes this way, going up against the wall, the ventricular wall, then blood is pushed up into the aorta and pulmonary trunk to get the blood out of the heart. So please note for me then this sequence: SA node, AV node, bundle of His, right and left bundle branches, and then up the Purkinje fibers. That's how the electricity that's made here spreads across the heart itself to activate the other muscle cells that require this kind of input. And another fact we should point out here is that at the AV node, there's something called the AV node delay, okay, of about 0.1 seconds. The spread kind of pauses here in order to allow for the atria to complete contraction before you activate the lower chambers. So this delay is important to allow for the upper chambers to get done before you activate the lower chambers. Otherwise, all four chambers will be squeezed at the same time. You can't have that. It's upper then lower. Okay, so that's a good significance of the AV node delay. Now, once this spreads around the heart, this electricity must then turn on the non-pacemaker cells. And so those non-pacemaker cells have their own type of action potential. I mean, the muscle cells, so they can certainly fire. So let's look at the action potential of your non-pacemaker cells, okay? So here, start around, say, around negative 80. So it comes up, goes way up, to around maybe plus 20 or so millivolts. pauses, and comes back down. Okay, so you have 3 phases here. Phase 1, phase 2, phase 3. And as you can see, this cell rests. When it comes down, it rests and waits again for a new input to come in. So these cells require an external input from your pacemaker system, versus these cells would have already drifted back up by themselves. So phase 1. So phase 1 is your depolarization phase, okay? That phase happens from voltage gated NA. So now we're back to normal. This is NA going in, creates that phase through voltage gated channels. This phase here is called your plateau phase. Okay? The plateau phase is due to calcium, voltage gated calcium channel. So here, calcium leaks in, but that Ca leaking in is being opposed by potassium leaking out. Okay, so Ca and K plus fight with each other, so that kind of makes it like a stalemate. So they plateau. Not much change is occurring there during that phase. And eventually the calcium gates close, and then the K gates will drive this process. So K out, Ca in, here's K out, and then in. Okay. So now in the repolarization phase here, your potassium out, so voltage gated Ca out is what will bring it back down to its resting level of around negative 80 or so millivolts, okay? So that is the action potential of your non-pacemaker cells, meaning the cells of the heart that squeeze it to create blood movement. Not the pacemaker cells. The pacemaker cells don't squeeze. All they do is just create electricity to turn these cells on, okay? Now, something else to point out here. So now when Ca comes in during the plateau phase, this Ca comes in, will trigger the SR to release calcium inside the muscle cell. Okay, that's called calcium-induced calcium release. This part, calcium-induced calcium release. So Ca in from the plateau phase will get to the SR and trigger the SR to release more calcium. Then that calcium, as well as this calcium, will allow for the cross-bridge cycling to occur. As you recall from cross-bridge cycling, you have your troponin here. Okay. So that troponin will bind to the calcium that's being released from the SR, and that will pull away the tropomyosin out of the way, like so, and that will expose your actin binding sites to myosin for cross-bridge cycling to occur. And as the heart muscle does its cross-bridge cycling, it squeezes because it's contracting. So that's how the heart squeezes, because you have triggered the SR to release calcium to unblock actin to allow for myosin to form cross bridges, and then to do the power stroke, detachment, again, activation, grabbing, power stroke, detachment. That cycle over and over and over, and as it does so, the heart will squeeze to push blood out. Okay, we'll pause there.